Okay, here's where it gets interesting. 4.3 is very important to the solution for a second order differential equation. We have in this section the three possibilities of a second order linear differential equation in terms of its solution and how that solution could look. Three possibilities. I want to talk about and cover those three possibilities with you today, and then give some problems to match each possibility. I want to be able to show you where some of the information comes from so that if you have a question about why this is, you will understand it. Now, I'm going to cover something here that I didn't cover in 4.2. In 4.2, the question would be, for me, is where in the heck did that formula come from? The formula is actually deduced by the procedure that's called reduction of order, which takes a long time to do. So I kind of cut through some stuff and said, we'll just use the formula. Forgive me that I did not cover all those steps in terms of how to get to it. It's very long. In this section, there are a couple of things that I will cover in detail to show you why this is, because I think that it's important for you to know why. And then the actual solutions of how to get the solutions would be very easy. But I think it's easy when you understand that what I'm doing and why I'm doing it, it makes sense. If nobody else understands it, you understand it. So let's see if we can go through it. The objective here to solve the nth order linear differential equation with constant coefficients. Constant coefficients simply means, look at this equation for number 2. See how it has a y double prime plus b y prime plus c y equal to 0. A, b, and c are numbers, constants, okay? So here we have a differential equation of whatever order, nth order. Here's second order, and the coefficients are just numbers. So if that be the case, then the way we solve that particular differential equation is going to be the same. So you can change those numbers up, and we have a model of how the solution ought to look like. We model the nth order, equation number 1, we model the nth order, equation number 1, based on the second order. Second order is it's like tangible stuff that I can touch, and okay, it's second derivative, we can deal with that. The nth order, that could be very difficult. But the way we solve the nth order will be the same way we solve the second order. Same idea. And so maybe today I can show you a third order, possibly a fourth order, and we'll see how we solve that. And the solutions would still be consistent with this model. So to solve equation 1, we first seek to solve, here what I say, the first order. Just let n equal 1 and look at that solution. If you let n equal 1, then the solution that you have, or the differential equation that you have, is a differential equation that has order 1. The highest derivative is just y prime. Right? So this is like y prime plus some constant times y equal to 0. We're still talking about homogeneous differential equation. So if that be the case, if you solve this, that's just separation of variables. And when you solve that guy, you get y is equal to some constant times e to whatever power times x. That helps us out. That tells us something. That tells us that if I have a differential equation of order n, doesn't matter what order, if it's order 1, order 2, or anything bigger, as long as I know that the coefficients are constant numbers, or constants, then my solution would always be exponential. E raised to some power. That's the key. Okay? That's the key. The point is this. The solution, exponential, always will be. If it's a linear differential equation with constant coefficients. Right? So assume then for equation 1 that the solutions are of the form, all the solutions are of this form, y equal to e to the mx. So then, if that be the case, then it doesn't matter if I have the order is 1, 2, 3, 10, 100, doesn't matter. I'm going to get exponential form. So let's look at the second order differential equation. Take this equation number 1 and just truncate everything bigger than order 2. So then I have some constant times y double prime plus some other constant times y prime plus c times y equal to 0. I want to solve that. Here's how we solve it. We solve it by assuming that the solution looks like e to the mx. So let y equal to e to the mx, and we can produce what we will call hereafter an auxiliary equation, equation number 3. Let me show you. So letting y equal to e to the mx implies that y prime is equal to m times e to the mx, and y double prime, yes, is equal to m times m, or m squared, times e, yes, to the mx. So what I'm going to do, I'm looking at equation number 2. I'm trying to solve this guy. That's our objective for today. Just give me the solution for equation number 2. That's what I'm going to do. If we can satisfy that, then we're done. And we can go eat something that's really good and healthy for us, right? Because I messed up over the weekend. So anyway. Mercy. You can't be short and eat a lot because it doesn't look so good afterwards. But anyway, so I'm going to take equation number 2, replace y with e to the mx, replace y prime with m times e to the mx, and then replace y double prime with m squared times e to the mx. And let's see what we have. So this is a times y double prime. That becomes m squared times e to the mx plus b times m times e to the mx plus c times e to the mx is equal to 0. I'm going to factor out the common term. The common term is e to the mx. Pull that guy out to the side. So I have e to the mx times brackets a times m squared plus bm plus c equal to 0. Now, it doesn't matter for whatever choice of m, doesn't matter for whatever choice of x. E to the mx is never equal to 0, right? So, since we know that for whatever choice of m or x, e to the mx is never equal to 0. Then a m squared, something has to be 0. If I have something times something else equal to 0, well, if the first something is not equal to 0, then the other something has to be equal to 0. So that means that a times m squared plus bm plus c equals to 0. This is the auxiliary equation. This is that equation here. So the goal then would be to find such values for m that would solve this. So can Can we find such values for m that solves equation 3? That's equation 3 there, right? How many possibilities of m? What kind of equation is equation number 3, first of all? Okay, it's quadratic, right? If it's quadratic, then how many possibilities of the value of m would take on? 3. Solution types. Solution types. Not the actual solution. Of course, we have at most 2 solutions, right? But we have 3 possibilities for those solutions. I can get 2 distinct solutions, I can get 1 solution, or I can get 2 imaginary solutions. Are you with me? You remember, if you take this quadratic equation and if you look at the discriminant, remember that b squared minus 4ac? We said there was 3 possibilities for that, right? It could be positive, it could be equal to 0, or it could be negative. This is algebra now, right? So I'm looking for some help here, you know. For DE, you're like, you know. But for the algebra, you say, oh yeah, man, I'm with you now, right? But you are like, that's algebra? Okay. Oh yes, it is. Oh, mercy. You all don't like me. I tell you, they don't like me. They don't like me, mama. Okay. There are 3 possibilities for the choice of m. Distinct means different, right? Repeated means you get the same value for m, or complex conjugate. If they're distinct and real, there's an m sub 1 and an m sub 2. They're different. That happens when the discriminant is positive. Do you remember that? If the discriminant is positive, that simply means for the graph, for that quadratic, that the quadratic function, the graph, crosses the x-axis 2 times. That's what this means. Okay? If m1 and m2 are the same, that really meant that the discriminant from that quadratic formula, what was under the radical, that discriminant was equal to 0. That means graphically that quadratic curve, it just touches the x-axis, right? So it either sits on the x-axis like a cup, or the x-axis is the top, the seal. The third possibility is that if the discriminant is negative, then that means that m1 and m2 are complex conjugates, right? And that simply means graphically that the quadratic curve does not even touch the x-axis. Is this kind of ringing a bell? A little bit? So let's see if we can show that. Here we have m equals to, I think we wrote it as a, b, and c for those coefficients, so that's good. So we have negative b plus or minus the square root of b squared minus 4ac all over 2a. So this is the b squared minus 4ac that we're referring to. So for the first possibility, if m1 and m2 are distinct, just say different, right? This means graphically, they got this feature here that I need to use. See if I can remember it now. This is it. It's not it. I don't need that one. This is it. Yes. It straightens my lines out. So. And that's pretty cool. So now I'm going to draw a curve. And M sub 1 and M sub 2. Two distinct or different roots for M1 and M2. The other possibility M1 is equal to M2. So they're real and they're equal. Right? Now for this guy, we call that the discriminant. B squared minus 4AC was positive. For this one, the discriminant, B squared minus 4AC, is equal to 0. And graphically, let's see if it'll recognize this curve. Oh, it's pretty. That is cool stuff, man, I tell you. Doesn't want to erase that, though. That's weird. More practice before you come to class. But anyway, okay. See if I can make that a Y. Good. So, that's the point there. So M1 is equal to M sub 2. Then the third possibility, no more space. M1 and M2 are complex conjugates or imaginary. So here our discriminant is less than 0. And so for whatever graph that we have, some parabola, it just never crosses the x-axis. And that's what that means. So for these three possibilities, we want to be able to write our solution. For the first part, it's very easy. When you take that quadratic equation and you solve for M1 and M2, if they're different values, then the solution is straightforward. So that's case number one, distinct real roots or different roots. Right? So under this assumption, you solve that auxiliary equation, you get two different values for M1 and M2. Your solution is automatically the complementary solution, y is equal to c sub 1 times e to the m sub 1 times x plus c sub 2 times e to the m sub 2 times x. Let's look at this problem right here. So I'm going to take this problem through the steps, but hopefully you see it in this first problem. And if you see it, you can kind of jump right to the auxiliary equation and go from there. It's a whole lot easier. Okay? But I'll just take this right from ground zero. So let y be the solution where here y is set to equal to e to the mx. And then just like from the proof that I gave, so y prime is m times e to the mx. Y double prime is m squared times e to the mx. So I take this problem, this is 4, I leave it there. Y double prime is m squared times e to the mx, plus this is y prime, so y prime is m times e to the mx equal to 0. Factor out e to the mx. You have left 4 m squared plus m equal to 0. This implies, because e to the mx is not equal to 0, that must be that 4m squared plus m is 0. We just solve for m. So you get m times 4m plus 1 equal to 0. This implies that m is equal to 0 and m is equal to negative 1 over 4. So these are my two distinct roots for m. So my solution, y sub c, is, see how they want us to write it, right here. Just going to write it in that fashion. My m sub 1 is 0, my m sub 2 is negative 1/4. So this is c sub 1 times e to the 0 times x plus c sub 2 times e to the negative 1/4 times x. And you can simplify that, so y sub c or y, whatever, doesn't matter, is equal to c sub 1 plus c sub 2 times e to the negative 1/4 x. All right. Is that okay? Now here's the quick part. Here's the quick way, I should say. Without even having to go through let y equal to e to the mx, you can skip that. You could have solved it in the world. You could have solved this guy by just jumping right to the auxiliary equation. And the auxiliary equation is just simply, wherever you see y double prime, basically it's going to be m squared. If you see y prime, it's going to be m. If you just have y, then there's no m. Right? So this is 4m squared plus m equal to 0. Well, isn't that the same thing as this guy right here? See that? So you can just go right to it. I'm fine with that. I take this problem and I just jump right to it if that's okay. So we say that this is not equal to, but it implies, because the auxiliary equation is m squared minus 36 equal to 0. Remember I said if it's y does not represent m. Right? For the auxiliary equation, y prime is represented by m. Y double prime, m squared. If it's y triple prime, m cubed. We just solved the auxiliary equation, right? This is the auxiliary equation. Please never say that y double prime minus 36y equals 0 is equal to m squared minus 36. Or look, don't say this. Don't say that. It's not the same. It's an auxiliary equation. It's not that equation. They're not the same. Okay? So just please be very careful. I don't want you to say it on the test, because if you say it's equal to that, then I'm going to mark it wrong. Because I want you to understand what we're doing. It's just not about a matter of just working some problems. Remember, wisdom is the principal thing, but with all thy getting, get an understanding. There are a lot of folk who are smart out there, have a lot of wisdom, but you got to have the right knowledge to be able to apply that wisdom. Oops. So we take the m squared minus 36. You solve that. That's m minus 6 times m plus 6 equal to 0. M is equal to 6. M is equal to negative 6. So y sub c is equal to c sub 1 times e to the 6x plus c sub 2 times e to the negative 6x. Any questions so far? Now you can have, doesn't matter about the order. Thought that was a higher order. Thought I had one to the third order. Must be on down further. Okay, anyway, let's look at this one. I'm going to go ahead and write the auxiliary equation. This is m squared minus m minus 6 equal to 0. So just factor m minus 3 times m plus 2 equal to 0. So m equals to 3 and m equals to negative 2. So y sub c is c sub 1 times e to the 3x plus c sub 2 times e to the negative 2x. Any questions there? Yes, sir. I haven't gotten to the other two cases. This is only case 1. Okay. Case 2. Thank you, Lawson, for helping us with our transition statement. I learned that in English, right? You got to have a transitional statement. But anyway. So our transition is that there are 3 possibilities. The first case, very easy, distinct roots. The next case is that the roots are said to be the same, or you have repeated roots or equal roots. If that be the case, then the solution looks like y equal to c sub 1 times e to the mx plus c sub 2, bless you, times x times e to the mx. But where does the x come from? That's the question. The x actually comes from, remember back in the previous section, we have give me a solution, I can find the other solution by using the formula. That's what they do here. So they if you have one solution, we can find the second solution, and the second solution is found by the formula. Now I want to show you, I need to show you how that comes about in terms of the second solution being x times e to the mx. That's important. Remember on the previous test, I asked you for one problem just to show me how do you derive P equal to C times E to the KT. Well, it might be the same situation here on this test. So. Okay, I shouldn't be laughing like this. Yes, Tyler. Yes. No, it's the same. They're both m sub 1. Yep, because it's going to be the same number when they're, if it's case number 2, here we have repeated roots or equal roots. So m1 equal to m2. So they just write m1, and I just write m. So look, so what they say is let y sub 1 equal to e to the mx. And I just write that, so I don't have to worry about dealing with the subscripts of m sub 1, and it's too small to write. So let this guy be the first solution. We use the formula to find the second solution. Okay, the test will be next Wednesday. Anyways, it'll take me a while to get through this stuff. So, so we use the formula to find y sub 2. Let's see. You need to go back and look at, this is a times y double prime, plus b times y prime plus cy equal to 0. And this implies then that y double prime plus b over a times y prime plus c over a times y is equal to 0. I did that to show you that, for that formula, you need that it's e to the negative integral of p of x. So we need p of x. So here, p of x is equal to b over a. So the formula says that y sub 2 is equal to y sub 1, just write the formula, times the integral of e to the negative integral, so p of x dx divided by y sub 1 to be squared dx. So our y sub 1 is e to the mx times the integral of e to the negative integral, I need p of x, that's b over a, times x over y sub 1 squared. So y sub 1 is e to the mx. This is e to the mx, all to be squared, dx. So y sub 2 is equal to e to the mx times the integral of e. Just go ahead and integrate that. I'm sorry, I integrated already. That's negative b over a dx. And then when I integrate, I get negative b over ax. Negative b over a times x. And this is over e to the power raised to a power. You multiply the power, so that's e to the 2mx dx. Okay. Well, this is e to the mx times the integral of e to the negative b over ax. Since they have the same base of e, then I can combine the exponents. So this is minus 2mx dx. But I have an m sitting here that is kind of unusual, right? Because everything else is like b, a, x, and that kind of thing. And so, let's see. Well, tell you how we deal with that. You remember we said that there's a couple ways you can do it. You can take the derivative and you get it, or we can just use algebra. I'll just stick with the algebra. You remember how we said here that the roots are repeated. And if the roots are repeated, your discriminant is equal to 0. Remember that? So look, we're looking at this guy right here. We have m is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. The case that we're dealing with now is that what's under the radical is equal to 0. You remember? We have repeated roots. That's case number 2. Repeated roots. Remember, that parabola only touches the x-axis. Doesn't cross, just touches at one point. Right? That means that m sub 1 equal to m sub 2. So our discriminant is equal to 0. Are we all together on that? Are we all in agreement? Okay. The discriminant is equal to 0. So here, since we have repeated roots, this implies that b squared minus 4ac is equal to 0, and that implies that m is equal to negative b over 2a. Right? Are you with me? See that? So then I go back and just replace that m up here with negative b over 2a. So y sub 2 is equal to e to the mx. Leave that guy as it is. He's not messing with us. But it's that m up here that's affecting this integral. I want to be able to solve this integral. So this is negative b over a x minus 2 times m, which is negative b over 2a times x. And this is all dx. So we simplify. This is e to the mx times the integral of e to the negative b over ax. Negative negative is positive. 2 divided by 2 cancels out. This is plus b over ax dx. Well, the numerator, not the numerator, the exponent here is just 0, right? Because they're opposites. So y sub 2 is e to the mx times the integral of dx. The integral of dx is just x. So this is x times e to the mx plus c. We just take y sub 2 to be x times e to the mx. So for case number 2, the complementary solution is always written as c sub 1 times e to the mx plus c sub 2 times x times e to the mx. Okay. So this is how we write the solution for this particular problem. Well, let's look at a problem and see how it works. All right, number 5. Remember we said that we can go ahead and just plug this into the auxiliary equation. So the auxiliary equation is m squared plus 8m plus 16 equal to 0. See if we can factor. Some of them you can factor. Some of them you have to use that quadratic formula. Some of them you have to use synthetic division. So. Uh-oh, did I hear somebody just pray? Anyway. Oh, that's good. That's good. You're getting close to my territory now. So this is m plus 4 times m plus 4 equal to 0. And so m is equal to negative 4 and m is equal to negative 4. So you see the repetition, right? The repeated roots. So then we write our answer, we go right to it because we know how that form is to look for the solution. We just got through working that stuff out. So y sub c is equal to c sub 1 times e to the negative 4x plus c sub 2 times x times e to the negative 4x. That's it. Yes, that's right. Unless you want to go through and do the proof on each problem, you know, right? And I'm saying here, now that we've gone through it and we understand where the x comes from, right? You just go ahead and just plug it into that form and you get the answer, and you're done. All right? 6 works the same. Let's look at a higher order. This is a third order. So look at the auxiliary equation. This is M auxiliary equation. This is M cubed minus 5M squared plus 3M plus 9 equal to 0. We use synthetic division. Yeah, I know, man. I should have discovered that a long time ago. But anyway, so we take the coefficients. This will be 1, negative 5, 3, and 9. So 1, negative 5, 3, and 9. You want to look at that coefficient at the end, just take its factors. So, plus or minus 1, plus or minus 3, plus or minus 9. I'm going to try 3. So bring down the 1. 3 times 1 is 3. Negative 5 plus 3 is negative 2. We get 3 times negative 2 is negative 6. 3 minus 6 is negative 3. 3 times negative 3 is negative 9. You get 0. That's what you want, a 0 there. Now, you could have tried 1 at first, but here's the thing. Whatever number you try, you want to end up with a 0 down here. So that 0 means that this 3 divides that polynomial. Right? And so we can write it, the auxiliary equation like this. This is M minus 3 times, this is 1 times M squared minus 2M minus 3 equal to 0. Now let's see if we can factor now that M squared minus 2M minus 3. So this is M minus 3 times M, let's see here, minus 3M plus 1 equal to 0. So a 1 would not have done it up here, but a negative 1 would have. So our roots would be M equal to 3, M equal to 3 again, and then M is equal to negative 1. So our solution, remember that second order solution is the form, is the model. So it doesn't matter if it's a higher order than 2. I still stick with that particular model. Let's see. So this guy here, you can write this solution form first. Doesn't matter about the order. C sub 1 times e to the negative x plus c sub 2 times e to the 3x plus c sub 3, guys repeat it, so it's the x times e to the 3x. Here's a philosophical question. We did the math, and so the math proves it, but why do you think that the insertion of x is necessary? Yes, exactly. Exactly. If you didn't have the x here, right, you know what you have? Linearly dependent. And we said the solutions go back to 4.1 for the superposition principle, that the solutions here, y sub 1, y sub 2, y sub 3, are supposed to be linearly independent. If for C sub 3 times, if it was just e to the 3x, that would be the same form as C sub 2 times e to the 3x, right? Well, they'll be the same. They'll be parallel. So they would not be independent. So the insertion of that x is most important for linearly independence, right? So everything is all still intertwined and connecting together, whether it's philosophically or mathematically, they both support each other, okay? Do the homework. There's going to be a couple of problems dealing with the complex conjugates that you may fumble over. I will cover that on Wednesday, and I will cover 4.4 on Wednesday. We'll review on Monday and take the test next Wednesday. Thank you. And for those 3 people that I said to see me after class, see me now, please.